So I'm happy to host this Beyond Diagonal RIS webinar today. It's the third in the series of webinars. My name is Edward Jorsvik, and I'm the Managing Director of the Institute for Communications Technology at TU Braunschweig. And today I'm very happy to introduce Dr. Yijie Lina Mao from Shanghai Tech University in China to you. So let us take a look at the CV. So Lina is an assistant professor at the School of Information Science and Technology in Shanghai Tech University in China. She received the bachelor engineering degree from the Beijing University of Post Telecommunications and Beijing engineering degree from the Queen Mary University of London in 2014. The PhD degree in electrical and electronic engineering department from the University of Hong Kong in China in 2018. Then she was a postdoc at the University of Hong Kong from October 18 to July 19, and a postdoc with the Communications and Signal Processing Group, the Department of the Electrical and Electronic Engineering at Imperial College London from August 2019 to 21. Her research interests include the design of future wireless communications and artificial intelligence-empowered wireless networks. She's a senior member of the China Institute of Communications. She received the Best Paper Awards of the IEEE International Mediterranean Conference on Communications Networking in 2023 and the Springer Eurasian Journal on Wireless Communications Networking in 2022. She's also exemplary reviewer for IEEE Transactions on Communications 21 and the IEEE Communications Letters 22 and 23. Currently, she's serving on multiple editor boards. One is associate editor for IEEE Communication Surveys and Tutorials and the IEEE Communication Letters. Furthermore, she is the lead guest editor of one special issue in the Transactions on Green Communications Networking. She was also guest editor for two other special issues in IEEE JSAC and IEEE Open Journal of the Communication Society. Regarding conference organization, she was a workshop co-chair for the 20 to 22 IEEE ICC and for the 21 to 23 IEEE WCNC and the 20 to 22 IEEE PIMRC. She has been a technical program committee member of many symposia on wireless communications for several leading international IEEE conferences, and she has been recognized at the world's top 2% scientists by Stanford University in 2023. And before we start the talk, here are the rules. During the talk, which takes about 50 minutes, the audience will be muted. And of course, you can type your questions at any time in the chat. Then we will have 10 minutes for question and answers. You can either raise your hand and we will unmute 2 to 5 people to raise questions. And we will choose 2 to 5 questions from the chat and ask our speaker if no one raises a hand. And now, please enjoy the talk.
Thank you. Thank you, Edward, for a nice introduction. Let me share my screen first. May I know if you can see the slides now?
Yes.
Okay, perfect. Thank you, everyone, for joining this third webinar on Beyond Diagonal RIS. And I also like to thank Bruno and Mattel for inviting me to give this talk. And the title of my talk today is Exploring the Potential Advantages of Beyond Diagonal RIS for 6G. So in this talk, I will introduce 3 recent works from my group and also my collaborators in Imperial College London on this Beyond Diagonal RIS. And if you have any questions during my talk, as Edward just mentioned, you can type your question in the chat box, or if you have any question after this online webinar, please feel free to email me. So here's my email address, and I will try my best to reply as soon as possible. All right, so here's an outline of today's talk. I will first of all make a brief introduction of Beyond Diagonal RIS. The major challenges introduced by BD-RIS will be summarized to motivate our following study. And then I will introduce the use of BD BD-RIS by deploying it at the transmitter side and also at the receiver side to show the advantages of BD-RIS that we have discovered. And also I will introduce an efficient beamforming or scattering matrix design algorithm for BD-RIS that we recently discovered. And in the end, I will conclude this talk and discuss some future research trends or directions of BD-RIS. And I will try my best to finish off them in 15 minutes. All right, so I believe you are all familiar with RIS, which is also known as Intelligent Reflecting Surface, IRS, and I will call it RIS throughout this talk. And here we give a very quick recap of RIS. So RIS is a digitally reconfigurable planar surface with massive, low-cost, passive reflecting elements. And this surface is reconfigurable and intelligent because the reflecting amplitude and phase shift of each element can be dynamically or collaboratively controlled by software. And a typical shape of this RIS is in this conformal large surface. And at the end of this talk, I will also show some other advanced RIS shape, which is not limited to this two-dimensional structure. So as we can see from the right-hand side figure here, that for any incident signal wave, RIS can adjust the phase shift and reflect the signal to the intended direction. So it therefore can reconfigure the wireless propagation environment. This is actually a very good or a very powerful capability because in 1G to 5G, we only need to we can only design the transmission network to adapt to the wireless channel. But now the paradigm is changed because we can now reconfigure the wireless channel. So here I briefly summarize some attracting benefits of RIS. We know that RIS can significantly reduce both the power consumption and the hardware cost because it does not have need to use any active antennas or configuring it with any RF chips. And RIS is also helpful to enhance our spectral efficiency by reconfiguring the entire wireless propagation environment. And RIS is very flexible to deploy. So it can be deployed at a base station side, at the relay or the user side. And the structures such as like building walls and the vehiculars can also be used to deploy RIS. And the last benefit I would like to highlight is that RIS is compatible with various 6G applications and systems because they only use to reflect the electromagnetic wave. So it automatically supports this full duplex and full band transmission. All right, so next I'm going to introduce this mathematical transmission model of different RIS variants. So we will not go into the details of RIS modeling from very basic physical perspective or microwave network theory. So here we directly show this mathematical transmission model. We know that the most widely known or studied RIS at this moment is this diagonal RIS or single connected RIS. So I will explain why we call it diagonal or single connected. And for this classical type of RIS, we can see from this reconfigurable impedance network illustrated here that each RIS element is independently controlled by a tunable impedance, and it's connected to the ground. So there is no interconnection between the elements. That's why we call it single connected RIS. And based on this reconfigurable impedance network configuration, we can then derive the scattering matrix. So this scattering matrix is a diagonal matrix. So that's the reason we call it diagonal RIS. And the many existing works also use this Yijie theta to represent each diagonal element because only the phase of this incident signal can be tuned if we assume there's no power loss for the reflected signal. And the signal model at the single connected RIS is also very simple. And here we consider X is the incident signal at the RIS, and X1 here is the incident signal at the first RIS element. Because here we consider diagonal RIS, so there is no inter-element connection. The phase of each incident signal is independently controlled by the corresponding RIS element. For example, for X1, it's only steered by this theta 11 one only. And we want to highlight here that according to the microwave network theory, if we consider a lossless reconfigurable impedance network, the scattering matrix should be unitary. So what does this mean? It means that the power of the reflected signal should be equal to the power of the incident signal. So the law of energy conservation holds. And in this case, for this diagonal rays with this diagonal scattering matrix, we can only tune the phase of the corresponding component, and the magnitude is unchanged. All right, so in the past 2 years, Bruno's research team initiates the study of the evolution from diagonal rays to beyond diagonal rays. So what is beyond diagonal rays? Basically, BD-RIS is a generalization of current diagonal rays that I just described to a more general architecture that embraces diagonal rays as a special case. And contrast to conventional diagonal rays that I just mentioned, where each element is connected to its own reconfigurable impedance and to the ground without inter-element connection, the primary novelty for this beyond diagonal rays is that it enables inter-element connection. And by this means, the scattering matrix will not be diagonal anymore. And it introduces more degrees of freedom to control the incident signal. And for lossless reconfigurable impedance network, BD-RIS can tune both magnitude and the phase for each component of the received signal. All right, so next I'm going to introduce two basic architectures of BD-RIS. One is this group connected RIS, the other one is this fully connected RIS. All right, so we first look at the transmission model for fully connected RIS. As I just mentioned, in fully connected RIS, each element is interconnected with all other elements. And we can see this reconfigurable impedance network here. The interconnection among all these elements actually introduces more tunable impedance. So here we only illustrate an example for a 4-element RIS example. But if we consider like these n-dimensional elements, all of these elements needs to be interconnected in this fully connected RIS. And based on this configuration, the scattering matrix is now becoming a full matrix, and it should satisfy the unitary and the symmetric constraints. And this unitary constraint is introduced because we consider a lossless, we assume a lossless reconfigurable impedance network. And this symmetric constraint is introduced because the reconfigurable impedance network is reciprocal according to this microwave network theory. All right, so here's the transmission model for this beyond diagonal RIS. The reflected signal of each RIS element now depends on the incident signal at all RIS elements. And based on this model, we can see that diagonal RIS is actually a special case for this fully connected RIS. Why? Because if we turn off or tune those non-diagonal elements of this scattering matrix to 0, this fully connected RIS reduces to single connected RIS. But of course, we know that, as I just mentioned, that fully connected RIS introduces this more configurable impedance and also more optimization variables within the scattering matrix. It, of course, introduces additional hardware complexity and also computational complexity. All right, to address the complexity issue, fully connected RIS is introduced. For this fully connected RIS, the RIS elements are divided into multiple groups. So in this figure, we consider that the RIS elements are divided into 2 by 2, in total 4 elements in one group. So we have multiple elements groups, and each group has 4 elements. And all elements in one group are fully connected, but there is no intergroup element connection. And with this configuration, the resulting scattering matrix becomes a block diagonal matrix. And each block is a complex symmetric and unitary matrix, and should satisfy block diagonalization, symmetry, and unitary constraints. And the signal model for these group connected RIS is therefore expressed in this way. And for the incident signal at the elements within the same group, the corresponding reflected signal will be jointly steered by the elements within that group only. And it's obvious that these group-connected RIS can achieve a trade-off between the performance improvement and the manageable complexity. And moreover, it can be considered also as a general model, then single connected and fully connected RIS, because when G is equal to 1, group connected RIS reduces to fully connected RIS, and when G is equal to N, group connected RIS reduces to diagonal RIS. All right, so here I give a summary of the 3 RIS architectures that I just described. As this webinar mainly focus on the a scattering matrix design or the passive beamforming design for this BD-RIS, so the summary I provide here mainly emphasize from the optimization perspective. In terms of the constraints to satisfy for the scattering matrix, as I just introduced, different RIS configuration should satisfy different scattering matrix constraints. And in terms of this optimization variable within the scattering matrix that we need to design, for single connected RIS, we only need to optimize all these theta n, so there are in total n variables. And for the scattering matrix, for the fully connected RIS, we know that this theta has n by n variables, but because it's symmetric, so we only need to optimize n times n minus plus 1 divided by 2 variables. And for this group connected RIS, for each theta g, it has n divided by g times n divided by g square divided by g variables, and each group scattering matrix is symmetric, so we can we only need to optimize n divided by g times n divided by g plus 1 over 2 variables, and there are in total g scattering matrices, so we end up with this number of variables. All right, in general, we can see that fully connected RIS can achieve the best performance than single connected and the group connected RIS, but of course, it at the sacrifice of a high implementation complexity. And the group connected RIS can achieve a better trade-off, and it's more flexible than the other 2 structures. And we can carefully design the grouping method so that it can reduce to the other 2 structure, or it can become a different RIS architecture that is beneficial to the network environment. So based on the simple overview for the 3 BD-RIS architectures, we here summarize the motivations and the goal of this webinar. And we all know that in order to achieve the advantages of using RIS in wireless network, the passive RIS scattering matrix and the transceiver design needs to be jointly optimized. And such problem has been widely studied by a large number of research groups around the world for this conventional diagonal RIS, but it remains not well unexplored for BD-RIS. And moreover, we know that, of course, for the feasible region of the optimization problem, for BD-RIS, it's obviously larger than the feasible region for diagonal RIS. But what are the exact performance gain we could obtain for BD-RIS? It remains unclear. So here I summarize some research challenges of BD-RIS from the optimization perspective. The first challenge is introduced by this complex symmetric and unitary constraint. So it's highly non-convex and making the entire optimization problem very challenging to solve. And for BD-RIS, we know that more optimization variables need to be designed, so it inevitably increases the computational complexity. So how to design efficient algorithms while maintaining a relatively good performance should be studied. And the third challenge of BD-RIS is that it introduces optimization differences. So it means that all existing algorithms for conventional diagonal RIS cannot be applied to BD-RIS directly. So how to design these optimization algorithms? All these optimization algorithms need to be redesigned. So the goal of this webinar is to explore the potential advantages of BD-RIS when it's deployed at the transmitter side or the receiver side. And we also want to explore the performance gain of BD-RIS over diagonal RIS when it's integrated with massive MIMO and RSMA. And we also aim to design efficient optimization algorithms to achieve relative good performance, but also maintain an acceptable computational complexity. And in the following two parts of the webinar, I will introduce 3 papers of BD-RIS, one with my collaborators in Imperial College London and 2 with my students in Shanghai Tech University. All right, so in the second part of this webinar, I will focus on the transmitter side BD-RIS and introduce this work led by Bruno's group. And we first summarize the 3 motivations of considering deploying BD-RIS at the transmitter side. The first motivation is the challenges of using or deploying a large number of active antennas at the transmitter side. So here I compare massive MIMO and RIS. We know that there are similarities and also differences between massive MIMO and RIS. For similarities, both of them are mainly used to design beamforming to enhance the system performance. And as for differences, for massive MIMO, each active antenna in massive MIMO should be connected with a RF chain. And even for massive MIMO with like hybrid beamforming, several antennas needs to share one RF chain. And in contrast, the RIS does not require RF chain or other baseband signal processing hardware. Of course, it cannot support this baseband signal processing. So massive MIMO has actually a much higher hardware cost than RIS. But of course, it also requires larger power consumption in order to process and emit signals. In contrast, RIS is passive and it therefore has a lower hardware and power consumption cost. And based on the comparison, we here summarize the 3 major challenges of using massive MIMO. So massive MIMO has a high hardware cost, also high energy cost consumption, and also low spectral efficiency gain. So the last challenge I mentioned here, I need to clarify is because that the transmission rate of massive MIMO is not always increasing linearly with the number of transmit antennas. Instead, it at most increases logarithmically with the number of transmit antennas when the number of antennas is very high. So the question we need to think about is how can we enhance the spectral efficiency performance and with a lower number of RF chain or with a smaller number of transmit antennas so that we can reduce both the hardware cost and energy consumption for the massive MIMO. So this motivates the study of RIS-assisted massive MIMO. And the second motivation for this paper is that many existing works have discovered the advantages of deploying RIS at the transmitter side. Well, at the beginning of this webinar, I have highlighted one of the benefits of RIS is that it can be deployed flexibly in the wireless communication systems. So in general, we can classify the deployment into this transmitter side RIS and also this user side RIS. And recent work have shown that those 3 advantages of deploying the RIS at the transmitter side. So the first advantage is that by deploying the RIS at a short distance from the transmitter, the higher signaling rate can be achieved, which therefore lower the signaling overhead. And for the passive beamforming gain and also the network coverage for the transmitter side RIS are also in general better than this user side RIS. This is because that this transmitter side RIS can serve all users, while for the RIS user side RIS, only users near the RIS can obtain passive beamforming gain. All right, so the third motivation is that the spectral efficiency achieved by BD-RIS that has been discovered can be much better than direct diagonal RIS. So the question we want to answer is that, can we use the transmitter side BD-RIS to address the challenges of massive MIMO? And with this question in mind, we start investigating the performance of transmitter side BD-RIS. And here is the system model that we considered in this paper. And there is one base station with L active transmit antennas and it simultaneously serve K single antenna users with the assistance of one passive beyond diagonal RIS with N-RIS elements. And the channel between the base station and this BD-RIS is modeled by this matrix E. So here we assume that the transmit antennas at the base station and also the RIS elements are placed in uniform planar array. So the channel is modeled in this way. For these GA and GR are the gaps between each active antenna and each RIS element at a given looking angle, which is this theta ij. And this dij is the distance between each active antenna and each RIS element. And the lambda here is the wavelength. And the channel between the user and the base station between the RIS and the user is denoted by this HK, and we consider spatial correlation here in this channel model. So RK is the spatial correlation matrix which captures the large scale fading, and HK bar here captures the small scale fading. And in this work, we assume that the direct channel between the base station and the user is much weaker than the RIS to the user link, so it's omitted. So the effective channel between the base station and the user is therefore this cascaded channel denoted by GK. So it's the channel between the base station to RIS and from RIS to the user K. Okay, and for this paper, because we consider massive MIMO, the protocol we consider is this TDD protocol. And in this TDD protocol, for this coherence time, we assume there are tau available channel uses within this time, and it's divided into two parts. One part is for uplink training, and because we consider TDD, so channel reciprocity is assumed within a coherence block. And once the channel is estimated, and the remaining time will be used for the downlink data transmission. And in this work, we are not focusing on channel estimation design for BD-RIS, so we consider a very typical channel estimation method, and we assume the channel between the base station and the RIS is already known at the base station, and for the base station to user channel, each user needs to send N divided by L times of pilot sequences, and the conventional MMSE estimator is considered. So due to time limitation, I will not go into the details for this channel estimation, and this is also not the primary contribution for this work. So we consider a simple multi-user linearly pre-coded scheme, and the K messages intended for the K users are independently encoded into K data streams SK, and each of them are linearly pre-coded based on precoder WK. And in this work, we consider a simple and the fixed pre-coding method of maximal ratio transmission. And so the precoder is aligned to the effective estimated cascaded channel. And this is a very typical beamforming method adopted in cell-free massive MIMO. And the power to each user K is defined by this row K. And here is the signal received at each user. Because in TDD massive MIMO, it's common to assume that each user is only aware of this effective ergodic pre-coded channel, which is this expectation over G K Hermitian conjugate transpose multiplied with this precoder WK. So the first term here is the intended signal over the known channel at the user side. And the second term here is the interference results from the imperfect CSI at each user. And the third term here is the inter-user interference, and the NK is the noise. Based on this received signal, we can then obtain this SINR lower bound and also the corresponding spectral efficiency or rate lower bound. And they are known as the hardening bound, and it can be considered as a performance metrics in many existing works on massive MIMO. And the target for our paper is also aimed to design this power allocation coefficients and the passive the beamforming for the BD-RIS, which is embedded in this GK, and we aim to design those two variables based on the hardening bound. But as I mentioned, that if the effective channel statistic, which is this ergodic precoded channel, is known at the base station, we know that this rho K, which is this power coefficient, can be very easily designed. However, for this passive beamforming design, it's still very challenging because it's coupled within the expectation of the effective channel. So what we want to do is now to design BD-RIS passive beamforming based on the channel statistics. The target now we aim to design this BD-RIS changes to minimize this cross-correlation between composite channel vectors of users to reduce inter-user interference. So here's the definition for the cross-correlation F theta. So it's defined as the sum of the ergodic composite channel gain. The reason we choose this objective function is because we consider MRT to precode user messages. So the user channel, so the precoder is aligned with the user channel. And this cross-correlation can also be considered as the inter-user interference. So the target of this BD-RIS passive beamforming design is to minimize this interference. And the formulated problem now becomes like minimizing the cross-correlation subject to the unitary constraint for fully connected RIS. Note that the symmetric constraint is not considered in this work to simplify the optimization. And for this problem, we can form an n-square dimensional complex default manifold, which is this one, and we can transform this problem into an unconstrained optimization problem based on the conjugated gradient descent method. We can solve this problem, and also we need to utilize some projection method to satisfy this manifold constraint. But I will not go into the details for this algorithm. All right, so once we optimize the BD-RIS passive beamforming matrix, we can then optimize this power allocation by maximizing the minimum spectral efficiency lower bound among users. And the sum power constraint is considered here with upper bound limit PT. And it's very easy to solve this problem. We can introduce lack optimization variables gamma here, and to represent the worst case SINR lower bound, we can equivalently transform this problem to this one, and the only known convexity in this problem is this SINR constraint. So we can use successive convex approximation to solve the problem, and of course we can utilize bisection method, because for a given gamma, the problem will become a simple linear feasibility check problem, and it can be easily solved, and we can search over gamma to obtain the optimal solution. So here we illustrate some numerical results. To assess the spectral efficiency of transmitter side BD-RIS, we compare it with this transmitter side diagonal RIS, and also compare it with conventional massive MIMO without RIS. So in the left-hand side figure here, we plot the average spectral efficiency when the number of RIS elements increases from 32 to 128. The number of transmit antenna is 24, and the number of user is 4. And we could observe that the BD-RIS, which is this green bar, achieves a higher spectral efficiency than the diagonal RIS. And moreover, one thing we observe is that the spectral efficiency of BD-RIS when n is equal to 32, the spectral efficiency is much better than the performance of diagonal RIS when n is 64. So with BD-RIS, we can use less RIS element to achieve a better spectral efficiency. This is helpful because it can help to reduce the computational complexity for BD-RIS by considering a smaller size for the RIS. And in the right-hand side figure here, we also plot the spectral efficiency when the number of transmit antenna increases from 24 to 48. And we could observe that when BD-RIS is which is this yellow bar, when the BD-RIS has 96 elements, and when the number of transmit antenna is 24, this yellow bar achieves a better spectral efficiency than the conventional massive MIMO, but with a larger number of transmit antennas. So this helps us to draw the conclusion that the transmitter side BD-RIS aided massive MIMO can achieve a better spectral efficiency than conventional massive MIMO with less number of active transmit antennas. And this is helpful to reduce the hardware cost and also the power consumption for massive MIMO. All right, so in the third part of this webinar, I'm going to talk about recent works in our group on receiver side BD-RIS. And in the first paper here, we initiate the study of synergizing BD-RIS and RSMA in order to understand the win-win performance gain they could achieve by integrating with each other. And the second paper here, we investigate a low complexity passive beamforming design for BD-RIS. So the parameters we consider here follows the one that I introduced for the transmitter side BD-RIS. Now we assume that the RIS is deployed at the receiver side. So the direct link between the base station and the users is also enabled. And the effective channel now becomes the sum of the direct link GK between the base station and the user, plus the RIS-assisted cascaded link. And the base station employs RSMA, which is one-layer rate splitting method to manipulate the user signals. And both single connected and fully connected RIS architectures are considered in this work. So here is a detailed one-layer linearly pre-coded RSMA transmission model. I will have a quick overview of it. And at the transmitter side, and the message of each user is split into a common and a private part, and the common parts of all users are combined into a common message and encoded into a common string, and the private parts are independently encoded into private strings. So each string is linearly pre-coded based on precoder W0 to WK and superposed for transmission. So from K user messages, we actually generate K+1 data streams. And at the receiver side, once each user receives the transmit signal from the effective channel, it sequentially decodes the common string and the intended private string with the assistance of one layer of successive interference cancellation to achieve partially decoding the interference and partially treating interference as noise. And based on this model, the transmission rate of each user is now split into two parts. One part is the rate of transmitting the intended private string SK, and then the other part is the contributed part for transmitting the common string SC. And assume perfect CSI at the transmitter here, we can obtain the achievable rate at user K to decode the common and the private string. And because this common string needs to be decoded by all users, the achievable rate should be the minimum at each user to decode the common string. And so the problem we are going to solve in this work is that we aim to jointly optimize this passive beamforming at the BD-RIS and also active beamforming at the base station with the objective of maximizing the system sum rate. So this part is the common rate and this part is the private rate. And we subject to not only the transmit power constraint, but also the symmetric unitary constraint for fully connected RIS, because we only consider fully connected RIS in this work. And obviously, this problem is very challenging to solve due to the introduced of this BD-RIS. So to solve the problem, we here consider a classical alternating optimization framework by iteratively solving the passive beamforming matrix optimization problem, and also the active beamforming optimization problem. And for passive beamforming optimization, we actually found that with a given active beamforming and the least passive beamforming optimization problem can be equivalently transformed into this problem. So here we transform the symmetric and unitary constraints based on the definition of the scattering matrix in microwave network theory. And X here denotes the reconfigurable reactance matrix, and 0 here is the reference impedance used for computing the scattering matrix, and it's set as a constant. And by substituting this first constraint, which is this theta here, into this objective function, and also we can define a symmetric matrix of X that satisfies this constraint. And then these two constraints can be removed, and the problem becomes an unconstrained optimization problem, but it's still non-convex. And we can utilize this Cauchy-Newton method to directly solve this unconstrained optimization problem. And with a given passive beamforming, the active beamforming optimization subproblem can be solved by many existing optimization algorithms of RSMA. So one typical method is this weighted minimum mean square error, and due to time limitation, both this Cauchy-Newton method and WMMSE are not detailed here. So here we illustrate the numerical results. In the left-hand side figure here, we consider a system model where the base station has 4 antennas and serves 4 users, and the BD-RIS has 32 elements, and we plot the sum rate versus SNR, and we can observe that when SNR is 30 dB, BD-RIS assisted RSMA achieved around 16% performance gain over conventional RSMA. It also achieves a 4.6 around performance gain over single connected RIS. So because we consider perfect CSIT and also underloaded scenario, so there is actually limited inter-user interference. And in this scenario, the capability of BD-RIS to manage this inter-user interference cannot be very clearly or illustrated. So it therefore leads to a relatively small performance gain of BD-RIS over RIS. And for this right-hand side figure here, we plot the sum rate versus the number of RIS elements. And we can observe that for this fully connected RIS-assisted RSMA, it achieves, which is this fully connected RIS-assisted SDMA, which is this light blue curve, it achieves worse performance than this single connected RIS-assisted RSMA when the number of transmit RIS element is less than 16. So in this region, we can see that the gain obtained by RSMA is more significant than the gain obtained by fully connected RIS. And when we do those two simulations, we found that using this AO algorithm based on Cauchy-Newton method to solve the BD-RIS passive beamforming and WMMSE to solve this active beamforming design is highly complex. It takes very long time to do simulation when the number of RIS element is larger than 32. So this actually motivates us to think about whether we can find some efficient beamforming design algorithms that can achieve relatively good performance. So here's a summary of the motivations for low complexity beamforming design. And besides the high computational complexity algorithms such as manifold or Cauchy-Newton, we also found those two existing algorithms in reference 1 and 2 that derive the closed form optimal beamforming solution for beyond diagonal RIS. However, we found that some limitations of these two works. And for the one proposed in reference 1, it's for a single user case, and it does not consider the direct link between the base station and the user. And for reference 2, it also mainly considers this single user case, and when it considers multi-user MISO scenario, the algorithm proposed in 2 is based on this L2 norm of the effective composite channel matrix between the base station and all users. And this can only maximize the largest singular value of this composite channel matrix. And moreover, to utilize the algorithm that they proposed, the transmit beamforming needs to be jointly designed to enhance the channel gain only. So what we want to focus is a general multi-user MISO scenario, and it can be more general than the two models considered in these two works. All right, so in this paper, we also consider the same system model as I just introduced for synergizing BD-RIS and RSMA. And in this multi-user MISO setting, both the direct link between the base station and the users and the cascaded link between the base station to RIS to users are considered. So the effective channel is considered in this way. But now we do not consider RSMA in powered base station. We want to start from the most basic transmission network and to understand how to design passive beamforming metrics effectively. So the first objective of our work here is to design the passive beamforming metrics of beyond diagonal RIS to maximize the effective channel gain, the sum of the effective channel gains among users. Note that this objective function is equivalent to the Frobenius norm of the composite effective channel metrics formed by the effective channel of all users here. And these Frobenius norms aims to maximize the sum of the square of all singular values for these composite channel metrics. And compared to the L2 norm, this Frobenius norm is therefore more favorable in multi-user scenario to enhance the effective channels for all users. And all the three RIS architectures that I just introduced at the beginning of this webinar are investigated, including fully connected, single connected, and group connected RIS. So the problem we aim to solve is to maximize this Frobenius norm of the composite effective channel metrics of all users subject to the RIS constraints for different RIS architectures. Obviously, this problem is rather challenging to solve since the BD-RIS constraints are highly non-convex. So in this work, we propose a two-step method to solve the problem. In the first step, we relax this non-convex constraint into a convex set and solve the relaxed problem in closed form. And in the second step, we project the relaxed solution onto the feasible solution within the non-convex set. So next, I will introduce the two steps respectively. And in the first step, we relax the non-convex constraint set of BD-RIS to a convex sphere set, which is this S. So how do we obtain this relaxed sphere set? This is achieved by focusing on these fully connected RIS constraints, and we remove this symmetric constraint, and we take the trace operation to this unitary constraint. By taking trace from at both left-hand side and right-hand side, we obtain this constraint. Because we know that fully connected RIS constraint is more general than the other two, than the single connected and group connected RIS. So all constraint sets that I mentioned for the three different architectures are becoming subsets of this relaxed sphere set. So the relaxed problem becomes in this form. And for this problem, actually, in the reference paper here, it's already been solved optimally. And here, based on this vectorization and eigenvalue decomposition. So here we illustrate a detailed method to deriving the optimal algorithm. And I will not go into very detailed, but I want to highlight the issue for these optimal beamforming, optimal algorithms. So the issue is that first of all, it needs to vectorize the beyond diagonal RIS passive beamforming matrix into a very high dimensional vector. And it requires eigenvalue decomposition of the same dimension as this high dimensional vectorized vector. And it also needs to utilize a bisection method to find the optimal dual variables embedded in this optimal solution. So the computational complexity for this optimal solution is like this, which scales with the n to the power of 6 times this iteration of the bisection. So it's of high computational complexity. So to derive a practical solution of this problem, we propose this closed form solution. The idea of deriving this closed form solution is very simple. That is that we use a gradient ascent because we consider maximization. So we call it a gradient ascent approach. But we do not have this iterative update for each for all potential points. We only update or calculate a one-step update at a point of theta is when the theta is equal to 0. The reason we choose this point is because that when the value of theta is 0, the initial result for this objective function is 0. So we do not need to generate any other initial value with bias. And based on this initial point, we can calculate its gradient, which it can be easily obtained in this formula. And for this gradient, we know that it's the favorable direction for us to update the matrix theta. And to ensure that this update theta is at the boundary of these convex sets, we then scale the solution by using based on this coefficient. And in the paper, we also show that this scaling can be considered as a step size of the gradient that satisfies certain rules. Okay, so here we illustrate, based on this obtained relaxed beamforming design, here we want to illustrate a very simple example to show that although for the relaxed problem, our proposed solution is worse than the optimal solution. But because for the original problem with this non-convex BD-RIS constraint, our proposed solution can achieve a much closer solution to the original convex problem. So here we consider a very simple scenario for the original problem. The RIS has only 2 elements and it satisfies this single connected RIS constraint. And we relax this constraint to this convex circle constraint. And based on this relaxed problem, we can then calculate it based on the optimal method that I just mentioned with high complexity, and the result is around 4.3. And we can also utilize the proposed method to solve the this problem, and the result, the objective function result that we obtain is 3.9. So obviously, the proposed method can obtained for this relaxed problem is worse than the optimal solution. But if we look back to this original non-convex problem, we can see that there are actually only 4 possible solutions. And for fx3, here it's the optimal solution for this non-convex problem. And we can see that our proposed method, even though it's lower than the optimal one for the relaxed problem, but it's closer to the optimal solution of the original non-convex problem. All right, so based on the closed form solution we derive for the relaxed sphere constraint-based problem, we then devise the projection method to project it back to the feasible solutions that satisfies the non-convex beyond diagonal RIS constraints. So here we define symmetric unitary projection. So we first respectively define the symmetric projection and the unitary projection. And for any square matrix C1, we here define the symmetric projection as 1/2 times Z1 plus Z1 transpose. And this symmetric projection is guaranteed to find the symmetric matrix that is closest to the original square matrix. And we also define the unitary projection based on the singular value decomposition of any square matrix C2. So for any square matrix C2, we can have this SVD result here. And we multiply U and the V conjugate transpose as these to form the unitary projection. And we also show that because we know that the product of 2 unitary matrices is another unitary matrix. So this operation is guaranteed to find a unitary matrix. And then this matrix is also the closest unitary matrix to the original square matrix. And based on these 2 projections, we then obtain the symmetric unitary projection. So for any square matrix Z, we we first manipulate it based on the symmetric projection, and then we do the unitary projection. And the output of this projection can always satisfy the symmetric and unitary constraint for the fully connected race. And in our paper, we also use this proposition 1 to show that this symmetric unitary projection is the closest point projection to the original Z. So due to time limitation, I will not go to the details to prove this proposition. And let's summarize the proposed algorithm for fully connected race. So in summary, to maximize this sum of the Frobenius norms of the effective channel of all users subject to the BD-RIS constraint, we first calculate the passive beamforming matrix based on this closed form solution, and then we project the relaxed solution so as to satisfy the symmetric unitary constraints of the fully connected race based on this projection method. And we also need to highlight that because here this projection is only suited for fully connected race. But if we want to do it for single connected race or group connected race, what we need to do is just to change this step 2 slightly to satisfy the diagonal and the block diagonal race constraint. But I will not go into details, but it's very simple as we illustrated in our paper. And here we also summarize the computational complexity of the proposed algorithm for fully connected, group connected, and for a single connected race. So obviously, this is much lower than the optimal solution-based method for the global optimal solution of the relaxed problem that I just mentioned. All right, so to show the effectiveness of the proposed algorithm, we here consider 3 algorithms for comparison. POP here is the proposed one, and the POO here is to use the global optimal solution proposed in this reference paper 1 to solve the relaxed problem and use the proposed projection method to find the feasible solution. And DD here is the algorithm proposed in reference paper 2 to solve the L2 norm maximization problem. So we could observe that for the fully connected race, which are these 2 lines, it significantly outperforms the single connected and the group connected race. And surprisingly, we found that the proposed algorithm, which is this light blue curve, it actually achieves better performance than the projections based on the optimal solution when the number of race element is large. So more importantly, the proposed algorithm attains a much lower computational complexity to achieve this appealing performance. To further understand the benefits of our proposed low complexity algorithm, we then focus on this sum rate maximization problem based on multi-user linear precoding. So this problem is a special case or special problem than the problem that we just formulated when we synergizing BD-RIS and RSMA. By turning off all those common strings, we obtain this sum rate maximization problem for multi-user linear precoding. So of course, we can use the AO algorithm that we proposed in that paper to solve this problem. But now we want to utilize the low complexity passive beamforming algorithm we just proposed. So instead of using AO algorithm, we now simply consider this 2-stage framework. In the first stage, we directly utilize the proposed low complexity passive beamforming algorithm to maximize the sum of the effective channel gain of all users. And in the second stage, with the derived passive beamforming solution, we then utilize any existing beamforming optimization algorithms to solve the pure transmit beamforming optimization problem. So it means that all existing algorithms proposed for transmit beamforming design can now be directly applied to this proposed 2-stage framework. So next, I'm going to show you some numerical results. And for the proposed 2-stage framework, at the stage 1, of course, we use the proposed low complexity method. And for stage 2, we will use 2 classical methods for the active beamforming design. One is the fractional programming, and the other one is the regularized zero forcing. And for the conventional AO framework, we consider 2 methods to deal with the passive beamforming design. One is this manifold optimization that we briefly introduced for transmitter side beyond diagonal rays, and also this Cauchy-Newton method that we introduced for when synthesizing BD-RIS and RSMA. And the active beamforming for both two baselines are solved by fractional programming. So we only consider fully connected rays in the following simulation because our intention here is to understand the performance that our low complexity passive beamforming design can achieve. So here are the numerical results. In both figures, we consider the scenario where the base station has 4 antennas and it simultaneously serves 4 users, and SNI is set to 20 dB. Surprisingly, we found that from this left hand side figure that the proposed algorithm, which is this light blue curve, achieves the same or even superior performance than these two baseline algorithms based on this conventional alternating optimization algorithm. And moreover, from the right hand side figure here, we can see that the proposed algorithm, which is this light and this red based on RZF, those two can significantly reduce the CPU time. So we think the primary reason behind this surprising result is that because the optimization problem for BD-RIS is highly non-convex due to the symmetric and unitary constraints. So the use of AO algorithm is prompt to fall into the local optimal solution, which is far from the global optimal solution. In contrast, for our proposed two-stage method, BD-RIS is used to shape and enhance the user channels, and the transmit active beamformers are used to enhance the sum rate. So it helps to find a closer solution to the global optimal one. All right, so in the end, let me conclude this talk and discuss some potential future research directions. So in summary, from the 3 works that I just discussed, we summarize advantages of transmit BD-RIS and for the receiver BD-RIS as follows. And then for the transmitter side BD-RIS, we not only found that it can enhance the spectral efficiency, but we also discovered that with the assistance of this transmitter side BD-RIS, the number of active antennas at the transmitter can be much reduced without influencing the spectral efficiency. And for this BD-RIS at the receiver side, we observe that this BD-RIS can not only boost the sum of the effective channel gain, but also increase the spectral efficiency. And by synergizing RSMA and the BD-RIS, we could achieve a better performance and get a win-win spectral efficiency gain. All right, so for the future research directions, we know from the recent works of BD-RIS that we can not only classify BD-RIS based on the characteristic of the scattering matrix into this single group and fully connected RIS, we can also classify BD-RIS based on the mode it supports. So there are 3 different modes. For the reflection mode, the incident signal can be reflected in the same site, so it only supports half space coverage. And all 3 previous works that I just introduced consider this reflection mode only. And for the hybrid mode, the incident signal can be simultaneously transmitted to the opposite side or in the same side of the incident signal. So this mode is also known as star RIS or intelligent omni-surface. So it can provide full space coverage. And for the fully connected RIS in this hybrid mode, the constraint it should satisfy becomes in this way. So this theta R and the theta T are 2 scattering matrices for reflection and the transmission. And the multi-sector mode generalizes this hybrid mode. So it divides the full space into multiple sectors. And the incident signal at any sector can be reflected and scattered to all other sectors simultaneously. So such mode can provide narrower beam width and therefore enhance the antenna gain. And for the fully connected RIS in this multi-sector, the constraint it should satisfy becomes like in this sum of the scattering matrix for each sector multiplied with its conjugate transpose, and this should be unitary. All right, so based on the previous summary of different variants of BD-RIS, we here summarize some potential research directions. So first of all, we can come up with a novel variant BD-RIS design by designing this interconnection between elements for catering different applications. We can also focus on optimization and signal processing perspective for different variants of BD-RIS. We can not only optimize the scattering metrics, as I mentioned in this webinar, but also optimize beyond diagonal RIS deployment, and which has not been well studied yet. And also we can consider machine learning based optimization, which is also very attractive direction to not only reduce the computational complexity, but also adapt to the wireless environment. And we also know that channel estimation is very important in RIS. So for BD-RIS, of course, it's in an important research direction. And we also know that BD-RIS is compatible with various emerging 6G technologies and systems. So we can therefore investigate the performance and the signal processing for BD-RIS assisted multifunctional networks, such as integrated communication sensing and integrated communication with this wireless power transfer, or even BD-RIS assisted task-oriented communication or federated learning to enhance the learning performance. We can also investigate BD-RIS assisted non-terrestrial communication and BD-RIS communication in new frequency bands. All these applications remain unexplored. So the last but not least, the prototyping of BD-RIS is also very important. We know that for conventional RIS, it has been prototyped by many research groups, and I believe that it's necessary and urgent to come up with the prototype of BD-RIS, and this will better to motivate all studies in this field. All right, so before the end of this talk, I also would like to use this opportunity to broadcast our recent special issue, although it's on RIS splitting multiple access. So if you are working on integrating RSMA and the BD-RIS, you are very welcome to submit your work to our special issue. The deadline is extended to February 15, and it's 1 week later from today. Okay, so this is the end of my talk today. Thank you very much, and comments are welcome. Sorry for the delay.